All right. Okay, so we're going to continue on with doing some more review of polar functions. This should all still be a review of what you learned last year. No? Okay. So polar coordinates in the plane are coordinates are written r comma theta, where your r is going to be the distance to the origin, and theta is going to be the directed angle from the positive x-axis, just like trig. And so there's two different planes out there. Well, there's more than that, but the ones we're going to talk about: Cartesian, that's the x comma y. We call it the Cartesian plane, named after Rene Descartes. Um, or we call it the rectangular. Right? Those are rectangular coordinates. 2, 2 means your x value is 2, and then your y value is 2. We can take this exact same point, but put it on the polar grid and define it in terms of r and theta instead of x and y. And so to find r, you use Pythagorean theorem, because r is that distance from, get a pointer, from the origin. So your r will be the distance from the origin to that point. Well, it totally corresponds with Pythagorean theorem, right? That's the hypotenuse there. So you do x, the square root of x squared plus y squared, and that would give you the rad 8, which is 2 rad 2. So my r is 2 rad 2. And then if you remember, when your x and your y values were the same value, that was my favorite angle, 45 degrees, or pi over 4. And so in polar, that's what it's showing, is that this distance from the origin to the point is 2 rad 2. And then the angle, the directed angle from the positive x-axis to that terminal side would be pi over 4. So in polar coordinates, this would be 2 rad 2, comma, pi over 4. And keep in mind, we're going to do some examples of it, but there's more ways to write this polar equation. Polar coordinates. Polar coordinates are not unique. This one point, I could have a different angle. Like if my angle was all the way down here, what would that be? 5 pi over 4. But then with a negative r, it would have told me to come back this way. So a negative 2 rad 2, comma 5 pi over 4 would give me the same angle. I could have went around and added 2 pi to it. So what would that be? 9 pi over 4. You could also do that angle if I had gone around and then more. You could have gone negative, right? Done a negative angle, but with a positive r. Anyway, there's lots of different ways of writing the same polar coordinate. All right, so let's start with finding rectangular coordinates for the points with the given polar coordinates. So I'm going to give you polar coordinates in r comma theta, and you're going to give me rectangular coordinates, which are x comma y. So if this is r theta, this is an easy one, so I'm just going to draw the picture for you. Pi over 2 is the positive y-axis, and then you would go 4 units out. So what's that xy ordered pair right there? Well, you didn't travel anywhere in the x direction, but you traveled up 4 units in the y direction. So that's just 0, comma 4 is your x and your y. Negative 3, comma pi. Okay, well, your angle pi, you would have started here and gone to the negative x-axis, but then a negative r says go in the opposite direction. So you would go 3 units here, your point would be there. And that point in x comma y would be, you went 3 units in the x direction, 0 in the y direction, so 3 comma 0. 16 comma 5 pi over 6. All right, so this one's a little more complicated, but remember 5 pi over 6 means you would start here and it would land there, right? And 16 is your r. And so I magically make this appear, but if you remember, and we do give you the formulas on a different slide. I don't know why we didn't give it to you first, but we didn't. So keep in mind, you can get your, and this works for all of them, x is equal to r cosine of theta, and cosine of 5 pi over 6 is negative rad 3 over 2. And so that would just be a negative 8 rad 3. And then your y will be 16 times sine of 5 pi over 6. And that would be 16 times 1/2, which is 8. So let's see if it's covering up. Yeah, it is. Okay, so let me erase I'll erase the markings I just did, but that's where we're getting the XY coordinates that we just got. Erase all ink, and boom, there we go. All right. We're going to do the same thing here. Let's see, negative rad 2 and then negative pi over 4. So a negative pi over 4 would have had you turn this way and along that angle, but then a negative r means you're coming out this way. So, yeah, there's your point, right? And your r is a positive rad 2 now. And so to get your x and y, x would equal negative rad 2 times cosine of negative pi over 4. Cosine of negative pi over 4 is a positive rad 2 over 2. So you end up with what? Negative 2 over 2, so that should be a negative 1. And then your y is r times sine of negative pi over 4. And that'll give you a negative rad 2 times sine would be negative. And so that'll give you a positive 1. So my x coordinate should be negative 1 comma positive 1. And look, it totally corresponds with, there's the dot that I put. Let me erase these and confirm what I did was right. Doot. Beautiful. All right, so pretty easy to convert from polar coordinates to rectangular. Not too bad. And hopefully that all looked familiar to you. It should all be review. Let's go the other way. We're going to find polar coordinates for the given rectangular coordinates, and we're going to find more than one. I say find 2. I'm going to list more than more than 2 for you, just because there's a whole bunch of them that could happen. All right, so keep in mind, given rectangular coordinates, so this is x is 1, y is 0. And so that point is right there. So that's an easy one. You can look at, okay, your r is 1 and your angle is 0. So one polar coordinate it looks exactly the same. It's just this one is x and y. This is r and theta. Not the only way, though. I could have gone around the circle, a full revolution, and it could have been r is 1 and theta is 2 pi. Yeah. Still not the only one. I also could have gone to pi, right? Gone on the negative x direction, but given a negative r value. Oh, okay, so I didn't give that one yet. All right, I also could have gone clockwise around the circle, right? Negative 2 pi would bring me all the way back here with a positive 1 would put me there. And then I think, yeah. Okay, so then pi would just bring you to the negative x-axis. You're over here, but then a negative r would tell you to go to the right and go in the opposite direction. So there's 4, we said give 2. There's 4 different polar coordinates that totally correspond to this rectangular coordinate. Negative 3, 3. So that means here and here, your x and y values are the same. And then figure out what your r is, right? You're going to do Pythag. And you would get square root of 9 plus 9, so the square root of 18, which is 3 rad 2. And then hopefully you recognize whenever your x and y values are the exact same numerical value, then it's a 45-degree reference angle, but in quadrant 2, so that's a 3 pi over 4. So that's one way. R is 3 rad 2 and 3 pi over 4. Another one would be if you had gone in the negative angle direction, right, had gone to negative pi over 4, you would have down here, but then a negative r would say go in the opposite direction, and it would put you there. That one, 7 pi over 4. If I went clockwise, counterclockwise around the circle to 7 pi over 4, it would have been coterminal with negative pi over 4. Yeah, these two guys are coterminal, so given a negative r value tells you to go in the opposite direction. You also could have done, what would that have been? This way, negative 5 pi over 4, and then with a positive 3 rad 2. That works also. 0, negative 4. Remember, that's your x, that's your y down there. Well, that's a r is 4, and your angle is, you could do 3 pi over 2. You could do negative pi over 2. Let's see which one I did first. I did the 3 pi over 2. All right, so going counterclockwise, that would be 3 pi over 2 with an r of 4. You also could have gone clockwise, and that would be an angle of negative. Why did I say pi over 4? I meant pi over 2. Sorry. Oopsies. Pi over 2, obviously. Oh, and okay, I didn't do that one yet. All right, so 3 pi over 2 with a positive 4. I also could have went just pi over 2, which would be here, and then a negative r tells you go in the opposite direction, so a negative 4. I could have gone clockwise, negative pi over 2. The r is 4. And what else could you have done? Doesn't matter, whatever. Lots of ones, yeah. You also could have gone all the way around and then added another 3 pi over 2 also. There's lots of ways. All right, 1 comma rad 3 means you are in quadrant 1 unit, rad 3. Hopefully, and then your r obviously would be the square root of 1 plus 3, which will give you 4. So your r is 2, which that means that your cosine would be 1/2 and your sine would be rad 3 over 2. That's a tall triangle, 60-degree reference angle, so pi over 3. Your r is 2, your angle is pi over 3. You also could have went all the way around to the third quadrant, counterclockwise. That would have been 4 pi over 3, but then a negative value would have brought you there. You also could have done 7 pi over 3 would mean that you went counterclockwise a full rotation, which would be 6 pi over 3, and then plus another 1 pi over 3. And there you go. I only said 2, but gave you more just so that you realize that lots of ways. Polar coordinates are not unique. The same point can be represented with actually an infinite amount of answers. You could just keep on going and doing lots of rotations. Your angles could be positive, negative. R can be positive or negative. So lots of different answers with that. All right, your notes on example 2. We're going to graph all points in the plane that satisfy this polar equation now. Now we're talking about polar equations, not just a coordinate. Coordinate will be a point. Now we got an equation, so it should be a shape. We changed the notes so that you're when you're drawing your circles, they're not teeny, teeny, tiny little circles. We just, r equals 2 is a pain to draw with a little tiny thing. R equals 4 is a little bit prettier. All right, so if r equals 4, what that means is your radius is 4. Your angle can be anything. And so that means when your theta is 0, you would go out 4 units and put a dot. And when your theta is pi over 6 and all the way around, your r is 4, boop, 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 it's a circle. Radius 4, centered at the origin. What happens when r is negative 4? All right, well, when your theta is 0, you would have been here, but r is -4 means you would have gone in the opposite direction and you would have put a dot 1, 2, 3 right there. And when your angle was pi over 2, that would have been here, but a -4 would have said, oh, you're going down here and putting a dot on the 3 pi over 2 line, right? And at pi, a -4 would have meant you would have come over here. And at 3 pi over 2, -4 means go in the opposite direction. So it turns out that you still have a circle with radius 4. Doesn't matter if your r is positive or negative, you've got a circle of radius 4. What about when they tell you theta equals pi over 6? All right, so that means r can be anything, but your angle is pi over 6. So you would be turning here, and you would, if r is 0, you're here, r is 1, r is 2, r is 3, r is 4, all of these guys. But r could be negative also, which means you got to go in the opposite direction. It's 2, and so it ends up being that ray, just going straight through the angle pi over 6. So that's what happens when you just have an r equals just a straight up number, or a theta equals a straight up number. That's how you handle those type of equations. And then we did the more complicated equations yesterday, or in the day 1 lesson, whatever day that was, where you did all those pedal graphs and lemniscates and all of the more complicated ones. These ones are the easier ones. All right, we can also do polar curves with our graphing calculator. And so you want to make sure you go into mode and you hit polar. And I watched that last video that I tried to show you my calculator, and I right now realize it was futile. I will not try to show you my calculator this time because you don't see jack crap. So, all right, so you go hit mode and then arrow down to where function, parametric, polar sequence is, and arrow to the right until you're in polar and hit enter. And then when you hit y equals button, you're graphing, when you put in the equation, it now says R1. So you'll hit sine of 6, and when you hit X now, oh look, it's theta. Oh, so pretty. All right, let's go to the window. And now instead of X min and Y min and all that, we got theta min. We're going to put 0. Theta max, you'll put 2 pi. If your theta max already says 6.28, blah, 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 you're already good. Theta step, we're going to put pi divided by 48. Otherwise, we got funky looking graphs. What happened, the theta step is like how many dots, how many angles do they plug in. And so if you jump around, it'll look very boxy instead of flowery, if that makes sense. All right, and then your X min, you should have as negative 1.5. Your X max should be a positive 1.5. Didn't say anything for scale, so I just leave it as 1. Your Y should go from negative 1 for the min and a positive 1 for the max. You can leave Y scale. Let's hit graph. Oh, by the way, the reason why we choose this window is you want your calculator window is in the ratio of, if you notice how, like, I'll show you the calculator here, wider versus the height, it's got a ratio of like 3 to 2. And so if you don't want your polar graphs to look distorted, then whatever X and Y values here you choose, you want, you know, a 3 to 2 ratio, 3 to 2 ratio on that. So that's the reasoning behind. I got dots instead of a straight line, so I'm going to fix that. Okay, graph. Oh, look at that beautiful petal graph. Hopefully you got the same thing. Isn't that so pretty? Oh. And if you look, how many petals do you have? Well, you had a 6 here, right? So you should have expected there to be 12 petals. And sure enough, 12 petals with just a radius of 1. So, all right. How about 1 minus 2 cosine theta? Hopefully you've practiced these so you recognize that, ooh, 1 in front, smaller than the 2. That's a loop-de-loop. Cosine, oriented on the x-axis, negative in between there means it'll be to the left. It'll be with like the negative x's, right? All right, so let's put that into our r. 1 minus 2 cosine of theta. And then are we going to do the same? Okay, so the only thing we're going to change, we're going to leave the thetas. And then we're going to change the x value, x min, to a negative 4.5 to a 4.5 for the x max. Leave the scale as 1. Y min, negative 3. Y max, positive 3. And again, hopefully you see that there's a 3:2 ratio on these guys. And graph, I should see a loop-de-loop. Yay! Isn't it nice when it totally conforms to what you already know? Beautiful. All right, how about r equals 4 sine of theta? Go back to y equals. And we got r equals 4 times sine of theta. And then thetas will stay the same for the window, but my radius is 4 now, so we want to go larger. We knew we need a minimum of 4, but we want that ratio of 3:2. So the minimum for x, I'll put negative 6. X max is positive 6. I'll leave x scale as 1. And then we'll go negative 4 to positive 4 for the y's. And hopefully before you hit enter, you just have 4 sine of theta, which that's a single circle. Your diameter will be 4. Right? And then sine means above, and it's a positive, it was a negative 4, so it'll be above. And there you go. It's got a radius of 2 and a diameter of 4. All right. Now I gave you the conversion formulas. Great timing, huh? Oh, well, hopefully they all look familiar to you anyway. All right, how to convert. X is equal to r cosine theta. Y is equal to r sine of theta. This is Pythagorean theorem. R squared is equal to x squared plus y squared. And then you can always find theta, especially you can always find it with this. Tangent of theta is y over x. I usually don't use this unless it's a cosine and sine values that I don't recognize, like they're not one of my special angles. But if they're a special angle, then you don't really need that. All right, so we're going to use these conversions to convert a polar equation, right, and into a rectangular equation. All right, so we're going to use the polar rectangular conversion formulas to show that this polar graph, r equals 4 sine of theta, ooh, that's the one we just graphed, is a circle. Now we're going to put it into a rectangular equation. We're going to make it into x's and y's, so that way we can show that it really is. It matches up. All right, so what do we know? R equals 4 sine of theta. Well, I know that since sine of theta, well, we know that's y over r, right? Well, we know y is equal to r sine of theta, which totally conforms with that sine of theta is y over r, which you should have learned way back in the day of opposite over hypotenuse, right? And so I'll replace my sine of theta with y over r. And then if you just multiply both sides by r, your r's will cancel here, and r squared equals 4y. And then, because we want everything in terms of x's and y's, but I know what r squared is in terms of x and y. It's x squared plus y squared. And is that obvious it's a circle? Well, it's not in standard form, so let's put it in standard form. We're going to subtract that 4y, setting it equal to 0. And then we can do the C word. We're going to complete the square on the y's. so that we can figure out where the center of the circle is, right? So if you remember I always draw little blanks to represent what I'm going to add to this y squared minus 4y in order to complete the square. And then I draw a little blank over here to remind myself whatever I add on the left-hand side, got to do it on the right. Don't have to complete the square on the x squared because there was not another x in your equation. You only have this extra y right there. Do you remember how to complete the square? You take the term on the y, the coefficient on y, -4, cut it in half. So that would be -4 divided by 2 would give you -2, and then you square it. And so squaring -2 would give you +4. Don't forget to add it to this side over to here too. And then now you have a perfect square binomial right there. X squared plus, this is a y minus 2, quantity squared equals 4. And hopefully you recognize that as the standard equation of a circle, where the center is at 0, +2. And it has a radius of the square root of 4, which is 2. Which totally matches up with that last example we did where we graphed r equals 4 sine of theta, and it was a circle up on the y-axis. Had a diameter of 4, but the center was right there in the middle with a radius of 2. Okay, one last thing. I'm going to give you some parametric equations of polar curves. And we're going to use those tomorrow. So I'm just going to give you the equations right now, and then you'll see how we use them tomorrow. All right, so parametric equations of polar curves. The polar graph of r equals f of theta. This means that they will have given you an equation where r equals some function of theta. Like they'll say r equals 4 sine of theta. That's an example of a function of theta, right? So you'll see ones tomorrow like that. And so if r equals some function of theta, it's the curve defined, and to define it parametrically, what we do is we know x is equal to r cosine theta, right? But instead of r, they will have given us some function of theta, so we're going to replace whatever they gave us here, this f of theta, we're going to replace r with it. And so we'll replace it with f of theta, and then you'll still have a times cosine theta. And then your y, we know, is r sine of theta. And then you're just going to replace this r with the function that they've defined, right? They will give you some function that's in terms of theta. And so f of theta times sine of theta. And there you go. All right, that is day 2. Mostly review, other than that last little bit, but we're not using that until tomorrow. Here's your homework, page 564, 1 through 29 odd, and then also 61. And yes, today's and yesterday's lessons were baby work because all of that was pre-calc. It should have all been review for you. And tomorrow is when we start actually doing calculus on these polar equations and graphs and all of that. Okay. I hope you all are having a fantabulous day. And come see me in office hours if you have questions. Yeah. Oop. This thing's a pain in the butt. All right, we got it. Okay, have a good day. Bye. Doo-doo.